So first, take some time, press pause, read through this, and try to figure out your answers. Okay, so the way I'm going to solve this, I'm going to look at this expression here because the question is asking me to rank the impulse. So here's an equation that helps me understand what impulse is. We start off with a certain momentum, and then in this case, the tennis ball is going to receive an impulse from the net because the net is going to exert a force on our ball, and as a result, the ball will have some final momentum. Now, in this problem, the balls are coming in with the same initial speed, so P initial is going to be the same in these three cases. The difference is P final. That's what's being described. And then based on what P final is, we can try to figure out what's happening with J. Okay. So if when the tennis ball hits the net and stops, we come in with some P initial, P final would be 0. So we only need enough impulse to bring this value down to 0. Okay, so kind of for part A, you can think J is kind of equal to negative P initial. For part B, I need my impulse to be big enough not only to bring this initial momentum to 0, but then to get some final momentum in that opposite direction. So if this is initially a positive value, this is going to be a negative value. So J has to be big enough to get rid of all that initial momentum and to give some negative momentum. So J is going to be an even bigger negative number. And then finally, a tennis ball that hits the net and continues traveling. Now we have some initial momentum, let's say to the right, that's positive. Here, I'm going to be still having a positive momentum, so it's not going to take as much impulse. I'm just, this impulse is just taking a little bit of that momentum away, but not enough to bring it to rest, just enough that it's still traveling in that positive direction. So B is going to require the biggest momentum, then A, and then C. Let's do another one. So press pause, read through this, and then press play to go through the answer. Again, I'm going to use this equation to kind of understand because they are asking me about the impulse. Now, each of these eggs, we're going to look at the impulse imparted to the egg that brings it to rest. Okay, so if they're all coming off of a table of identical height, the momentum they have right before they hit the ground is the same in all three cases. This is the momentum they have right before they hit the ground. And then also, the final momentum each one has is the same because they all end up at rest. So their final momentum is 0 for all of them. That means that J is the same for all of them. The impulse is the same in each case. Now you might think, how can that be? Because what happens in A, definitely the egg is going to crack. And what happens in C, the egg is not going to crack. So that might make you think that A, there's a bigger impulse in A. That's not true. The impulse is the same because all we need is an amount of impulse required to bring that object to rest. They all have the same velocity right before they hit the ground. So they all require the same amount of impulse to come to rest. The difference in these three cases is the time that it takes for them to come to rest. And in that case, we would consider that the impulse is equal to the average force times delta t. Delta t for this one is huge compared to delta t for this one. That means the force in this case is smaller compared to the force in this case. Okay, so let's look at that. And I'm going to just say this. Bringing an object to rest requires a certain impulse. In the previous example, the impulse was the same because we were bringing the same objects at the same initial speeds to rest. So when you're considering what the impulse is, those were all the same, but impulse is equal to the average force times delta t. And in those three cases with the egg, delta t was different, which means the force on the egg was different, which is why sometimes it cracked and sometimes it didn't crack. So if you can increase delta t, this average force that's required to bring something to rest will be very different. And it will be smaller. Sorry, if you increase delta t, this average force will be smaller. So a lot of our safety precautions that we take in our daily lives, what they do is they increase what delta t can be to bring you to rest. So for example, if you think about an airbag, what is the purpose of an airbag? Well, your body is going to experience an impulse no matter what, because you have some initial momentum and your final momentum is going to be 0. Like if you hit something, eventually you're going to be coming to rest. So no matter what, that you have a certain delta p, you're receiving a certain impulse. But what we can do is increase the time that it takes you to come to rest. And by increasing delta T, that decreases the force on your body. So the airbag allows you to come to rest over a longer period of time. The same with the safety net. When you fall and you hit a safety net, your body comes to rest over a much longer time than if, heaven forbid, you fall and land on the sidewalk and your body comes to rest in a very short amount of time. J would be the same in those two cases, but the force on your body would be very different. The same happens with the bungee cord, okay? The time that it takes your body to come to rest with a bungee cord is very, very, very long. So the average force on your body in that case is very small. It's considered pretty safe for your body.